Hello, I'm Farseen from MLabs. I'm excited to present the closeout report for the Fund11 project, CTL footprint reduction. CTL is a widely used library in the Cardano ecosystem. It is one of the major tools used to interact with the Cardano blockchain from off-chain code. CTL depends on the Cardano serialization library, CSL, and a few other Rust libraries for its core functionalities. This ends up significantly inflating the bundle size of CTL. CSL adds about 2 megabytes, while the Cardano message signing library, CMS, adds another half a megabyte. These two combined add significant delays to web apps which use CTL on the front end. It also complicates the bundling of projects that depends on CTL because there are some bundlers which doesn't play nicely with the WebAssembly binaries that needs to be bundled along with CTL. We entered this project because we felt that if we remove these WebAssembly parts, not only we can reduce the bundle size that our users need to ship over the internet, but also provide a much simpler build pipeline that doesn't have to deal with any WebAssembly binaries. We started with the goal of replacing CSL, the biggest binary which is crucial to the functionality of CTL, but is also the biggest offender, with a JavaScript or TypeScript replacement, while moving other smaller WebAssembly binaries like Cardano message signing library into their own optional packages. To replace CSL, we explored a few approaches. At first, we considered using an existing JavaScript SDK like the Cardano JS SDK, but we realized that it's going to be really hard and a lot of effort because the Cardano JS SDK has a completely different API from CSL. CSL is used extensively from CTL, so it would be a lot of effort to rewrite all of those usage size to use the Cardano JS SDK. So we ended up trying to manually port CSL to JavaScript by reading the Rust code and then handcrafting the equivalent JavaScript code. As we spent more time doing this, we realized that this won't scale. There are hundreds and thousands of functions defined in hundreds of classes. It would take too much time to do this by hand, and we would never have a complete port by the end of this project. Then we realized that the CSL classes and functions have a pattern. We can categorize these different um, classes and functions into a handful of templates. So we wrote a code generator that accepts a YAML-based domain-specific language to output TypeScript code that is API compatible with CSL. This was a huge success. We were able to completely automate the generation of the TypeScript library, and during this course of project, the Conway release was finalized, and we were able to quickly adapt our DSL to include the new domain types without any manual work involved. We also built an automated test suite that parses the CSL type definitions and our library's type definitions to check that they all have the same function names and all of the functions have same return type, argument types, and the same number of arguments. This helped us catch a few subtle edge cases that we had in the CSL API and made our API as close to CSL as possible. We also built an automated test suite where we checked every object we defined can be serialized to the same value as CSL. Once the biggest elephant, CSL, was taken care of, we started moving the other dependencies, which are less commonly used, into optional modules. With all of these combined, we achieved around 30% reduction in the bundle size of CTL. Now let me demonstrate the difference in bundle size between the old version of CTL and the new version of CTL, where we replace the WebAssembly binaries with our new library. Let me clone the CTL repo. Let me switch to a commit that is before the integration of the new library. Okay. Now let's use the example project provided by CTL. Well, that is bundling. Let me demonstrate the newer version. Let me start bundling the new version. So here the first version completed bundling. Let's examine the output. You can see that the WebAssembly libraries are present and they add about 3 megabytes combined to the final output. Now, when used in browser context, these are usually gzipped. We can see that the combined output is 1.5 megabytes. And in this version, it's only a single JavaScript output. The uncompressed size is 5.6 megabytes compared to around 7.5 megabytes in the previous case. And if we compress that, you can see that the output is compressed to less than a megabyte. That is a 33% reduction in the final size. That's all from the project, and thank you for your time.